Hi everyone. Welcome back to Dave's Math channel. I'm your host David Tare. Haven't made a video here in a few days. I figured it's time I made another one. And I think I'm going to resume, at least for now, my series on number theory. And today I'm going to talk about multi-perfect numbers. They're also known as multiply perfect numbers. Anyway, let's begin. So, what are these things we call multi-perfect numbers? Well, they're kind of a natural extension of perfect numbers. I think you guys all know a perfect number is a number such that the sum of its non-trivial divisors is equal to the number itself. I think you guys all know 6 is the smallest perfect number. After that, 28. After that, they get very, very rare. Although there's 51 that are known, and it's suspected most mathematicians would believe there's infinitely many. Um, but we can define multi-perfect numbers kind of similarly. If you look at this function we call sigma n, this is what's known as the sum of divisors function. This is the sum of all the divisors of n, not just the non-trivial ones. That means we have to include n itself. And if you include n itself, if you consider perfect numbers, we know that perfect numbers are the sum of all the non-trivial divisors. In other words, the sum of all the divisors of n other than n is equal to n. Well, if you add n, then of course the sum of all the divisors is equal to 2n. So another way of defining a perfect number is just a multi-perfect number of multiplicity 2, if you want to think of it that way. If you define multi-perfect number, sigma, this is how they're usually defined. You say a multi-perfect number is a positive integer n, such as sigma of n is equal to kn for some positive integer k. So then you can just think of perfect numbers as multi-perfect numbers with multiplicity 2, like I just said. And what about multiplicity 1? Well, there's only one positive integer with multiplicity 1, namely 1 itself, because 1, the only divisor of 1 is 1. That's kind of a trivial case that nobody really cares about. Usually we define multi-perfect numbers to have multiplicity at least 3. That excludes the trivial case of 1 and the case of perfect numbers, which we usually don't call multi-perfect. So what about higher multiplicities? You might wonder if there are any. Well, it turns out there are, but they're pretty rare. And I'll just show you some tables here. So this is all actually this is believed. These are believed to be complete lists, if you can believe that. So, like I said, most mathematicians suspect that there's infinitely many perfect numbers, even though they're very rare. But multi-perfect numbers turn out to be even rarer. For instance, it's known that there's only 6 multi-perfect, if there's no odd perfect numbers. This is all assuming that there's no odd perfect numbers, and most mathematicians believe there are no odd perfect numbers. If odd perfect numbers exist, I did another video on this about a month ago. If odd perfect numbers exist, they have to have at least 2200 digits, and they have to have a lot of other kind of unusual properties. Like they have to be equal to a prime times a square, and they have to have at least 10 distinct prime divisors. So most mathematicians suspect that odd perfect numbers don't exist. None are known. And if there's no odd perfect numbers, then these lists, these 4 lists on this page, on this slide, they're not just all the known multi-perfect numbers of multiplicity up to 6. They are all. These are complete lists. So you can see there's not that many. I mean, there's only 6 of multiplicity 3. I haven't counted how many there are of the higher multiplicities, but it looks like there's less than 20 of multiplicities 4, 5, and 6. Of course, they get really big. The higher the multiplicity, the larger the numbers that have that multiplicity, which kind of makes sense if you think about it, because it's hard for a small number to have a high multiplicity, right? I mean, you'd have to have a lot of factors, and most small numbers don't have that many factors. But the bigger numbers get, the higher their multiplicities can get. They just have to have a lot of small prime factors. Anyway, so these are the known. These are all the multi-perfect numbers of multiplicity up to 6, assuming there's no odd perfect numbers. If there are odd perfect numbers, then there are more of these. Anyway, and what about higher multiplicities? Well, it's kind of interesting. The number is the multiplicities grow. there's good theoretical bounds on how many there are. I think they're believed to be a finite number of every multiplicity. I don't think this has ever been proven, but I think it's strongly suspected that for every multiplicity, there's only finitely many multi-perfect numbers of that multiplicity. The number grows. I mean, it's already suspected that there's at least 10,000. I think it's 10,000 multi-perfect numbers of multiplicity 11. And this turns out to be the highest known multiplicity. There's only two known. What's interesting is that there's only two known multi-perfect numbers of multiplicity 11, even though there's quite a few of lower multiplicity. Yeah, maybe the list I showed before aren't complete because it looks like there's 36 of multiplicity 4, 65 of multiplicity 5, and 245 of multiplicity 6, and so anyway, but then the number grows, and it's funny, interesting for multiplicity 7 and 8. It's believed that these lists are complete, but it hasn't been proven yet. It's been proven up to multiplicity 6 that we have complete lists of all the multi-perfect numbers of those multiplicities. But then for seven and greater, we're not sure that we found all of them. And for 9 and greater, almost certainly we haven't. So it's even known that we haven't, I guess. So it's known that there are more multi-perfect numbers of every multiplicity, at least 9. And I don't know if it's ever been proven that they can have arbitrarily large multiplicities. Um, I think they probably have. I'm not sure, but we only know up to multiplicity 11. It's also known there's only finitely many of every multiplicity. So they're pretty rare. And I think this is a nice graph. This is the one I showed on the cover slide. This is a kind of a graphical representation of how many multi-perfect numbers there are of, or at least that are known of every given multiplicity. And this starts at 2. Notice it starts at 2. These are in yellow. They're a little hard to see, but these are all the perfect numbers. And it's suspected, like I said, it's suspected there's infinitely many perfect numbers. There's only 51 that are currently known. I think they're the 51 yellow dots here. And the largest is pretty large. I mean, if you look at the scale on the x-axis, is the natural logarithm of the natural logarithm of the number. So these things get really, really big. I mean, the largest known perfect number has ln of that number is already 17. And I guess e to the 17, what is that about? Maybe, I think it's in the millions. So that means that, yeah, it's like e to 1 million roughly, or e to several million. I know it's 2 to like 83 million or something. So these things are huge. The largest known perfect numbers are humongous. They have over, I think the largest known one has almost 50 million digits. But if you look at the higher multiplicities, like 3, I said there's only 6. You just believe there's only 6 multi-perfect numbers of multiplicity 6. They're all these 6 green dots. And the biggest of these isn't really that big. It's the ln of that number is a little over 3. And I guess, I'll save myself some mental exercise by just looking at the size of the number. I have it on the slide. This is a complete list, by the way. So the largest largest multi-perfect number of multiplicity 6 of 3 is 5100118016 11 digits. That means it's in the billions, but it's not in the trillions. So it's pretty large, but it pales by comparison with the largest known perfect number. And then they get bigger and bigger for bigger multiplicities. I mean, if you look at the blue dots as multiplicity 4, the ln of those numbers is already going up to almost 5. I don't even know if I want to try to figure out how big these numbers are, but they get much, much bigger. You can see that. But another interesting thing is happening. Notice that although these numbers with the higher multiplicities are getting bigger, they also seem to be getting rarer, or at least the ones we know are. I mean, like the theoretical bounds, like I showed you earlier. Um, where was that? Yeah, these were the theoretical bounds. It's suspected that these higher multiplicities, they get more and more of them, even though most of them aren't known. So they do get bigger. And probably, I think when you go beyond multiplicity 7 and 8, these points that are shown should be wider than they're shown because they're only showing the known ones. And this is only 2 dots for multiplicity 11, and it should be a lot more. I mean, there should be finitely many, but a lot more than just two. So interesting. And it almost looks like maybe there is a limit on their multiplicities. I don't know. I'm not an expert on this. But I think these things are really interesting. And there's just one more thing about what I want to say about multi-perfect numbers. We can define them in different ways. We can actually define different types of divisors of integers. We don't have to look at all the divisors. We can look at special types of divisors like unitary, biunitary, and infinitary. I don't want to define these in this video. Kind of beyond the scope of these video. I've actually looked into these a little bit. You don't have to even just. I'll probably do another video on these, maybe in my next one. But once you have these different types of definitions of different types of divisors, you can actually use those definitions to redefine, everything we've looked at with ordinary divisors, like perfect numbers and multi-perfect numbers. Not only that, but abundant and deficient numbers. Abundant numbers are numbers where the sum of the non-trivial divisors is bigger than the number. Deficient, the sum of the divisors is less than the number. You can define the same kind of things for these different types of divisors. You can also define amicable and sociable numbers, sociable chains. I talked about amicable pairs and sociable chains in another video for the ordinary divisors, but you can define them for these different other kinds of divisors. And I think the last thing I'm going to say in this video, I actually made a pretty important mathematical discovery maybe 20 years or so ago. I don't know how many people know about this. Probably very, very few people know this. But I think it was when I was working at Wolfram Research, maybe Raytheon, I can't remember where I was working. I did a little bit of number crunching, which I like to do. And I actually discovered the first, I think it were infinitary divisors. I discovered a sociable chain of, using the infinitary divisor definition, a sociable chain of length 7. And I believe it's the only one that's known. And I don't think there's any sociable chain with ordinary divisors known of length 7. So I got my name on a website for doing that. Maybe you'll find me on there. I don't know. These numbers were pretty big. I remember they had 14 digits each. Um, so anyway, just a discovery I made. Guess I'm tooting my own horn a little bit here. But anyway, I guess that's all I have to say in this video. Thank you for watching. Long live math, and I'll see you guys next time. Bye.